So first, a little bit about who I am. I'm a lead consultant at a company called Cognizant. If you're not in the consulting game, it's exactly like normal cloud-native software development, but you get to say the words, it depends, so much more. My primary remit is helping clients digitally transform, which can be a bit of a nebulous topic, but basically it's about making sure that clients are using technology in the way that provides the greatest operational efficiencies. And so I come from a cloud-native software and security background, and I'm the holder of a lot of opinions. Some of them might even actually be useful, but let's hope that the Venn diagram between useful ones and the ones that are in this talk is close to a circle. And my postgrad qualifications are in electrical engineering, so low-level languages will always be my first love. Also, on Friday, I just released a book called Cloud Native Anti-Patterns. So if you're really interested in all the things we've seen people do in the past that is absolutely horrifying, give it a read. And so the concept for this talk started with an idea I had, right? I wanted to know what was the weirdest language that could possibly be run on AWS Lambda. And unfortunately, I made the decision of picking the language before seeing if it could be run, which resulted in a lot of painful development for me, but hopefully a little bit of enjoyment for you guys. And so to cover off what we're going to be talking about, right? First, we'll explore what custom runtimes are, and then we'll dive into the different ways we can build them. We're going to explore 4 key ways we can build them, right? So the first way, you can create a custom runtime that acts as an interpreter or hosts an external runtime, allowing your code to run as if it's in its native environment. You can use an external binary to extend the functionality of your Lambda functions beyond what is typically available. You can use a library shim, and this is a bit of a workaround where your custom libraries can interface with the Lambda execution environment, enabling a little bit more flexibility. And then finally, we've got the self-contained runtime, where we use absolutely nothing that AWS gives us, and we take on full responsibility for everything ourselves. So first, unfortunately, we all have to do the homework. What are custom runtimes? So custom runtimes allow us to run development artifacts that are not natively supported by AWS Lambda. Imagine being able to leverage your existing code and libraries, or even experiment with the latest technologies without being restricted by the Lambda platform's default options. By using custom runtimes, you not only expand the tools at your disposal, but you can also tailor the environment to meet your specific needs. And this makes it a really powerful feature for developers who are looking to apply the advantages of Lambda to tooling that may not be natively supported. And so if you look at everything that Lambda supports, we've got quite a few options up there. We've got a couple of versions of Node.js, 5 versions of Python. If you really dislike yourself, you can run Java in Lambda. We also have .NET, Ruby, and right down at the bottom here, we've got these OS-only runtimes, provided AL2023 and provided AL2. And these are some fun little tools that are going to help us later, right? And even though this may seem like a pretty exhaustive list, if we go to the Wikipedia page and look up how many programming languages there are, yes, much like JK's list, this one is intentionally small, there are a lot. So the chances of your favorite tool or language, unless it's one of the main ones, being in Lambda, might be slim. And so when we look at Lambda versus service, there are compelling reasons why I would want to use AWS Lambda. Firstly, Lambda is simple. It allows us to focus solely on the code we produce and abstract away all the complexity of running it. Secondly, they're event-driven. We can plug into an extensive range of events within AWS that can trigger our code. And then they're also highly available, scaling in and out as required, all the way down to 0, and all the way up to thousands of functions at the same time. And finally, they have consumption billing. So if we've got spiky workloads, or we're not using it all the time, then we're not paying for a service sitting around doing nothing. And also, we only pay for traffic that we use during high traffic periods. On the other side, we could use services, and services allow you to bring your favorite language. They allow you to use specialized libraries to complete tasks that you may not be able to complete in the languages available in Lambda. They also offer you the greatest flexibility when it comes to deploying your code. And custom runtimes sort of give us the best of both worlds in this scenario, right? We sort of get all of these properties that make each of these individual options attractive in one package. And now, so far, custom runtimes might seem like a bit of a silver bullet, and we should be using them all the time, right? Because we can do whatever we want in our Lambda. But they don't come without their own drawbacks. So you really need a compelling reason for a custom runtime to be used. And usually, that reason is that you have existing code or existing libraries that need to be plugged into the Lambda event system and run on an ad hoc or spiky basis that may not be supported by Lambda natively. So to illustrate this point, these are all of the AWS services that you can use to trigger a Lambda function. We've got Kinesis, step functions, elastic load balancers, API gateway, Cognito, I'm not going to go through all of them, just kidding, and all sorts of other services, right? And all of these services drive Lambda from a push perspective as opposed to a typical container service in AWS that would either use a polling subscriber system or HTTP requests and webhooks to get information from these sources. But to understand what we're about to do, we need to go through a little bit more background knowledge, because much of our experience with Lambda is submitting our code to Lambda, Lambda running our code, and then us receiving a response. But what actually goes on behind the scenes is a little bit more complex than that. So here's a relatively basic conceptual model of Lambda. We can think of AWS as the source of all of our events, regardless of whether it's from HTTP or some other source, because the HTTP is proxied through the event system anyway. But basically, once Lambda receives an event and there's a new event to be processed, Lambda, in response, instantiates or unfreezes a container containing our runtime and our code. In this scenario, AWS provides the runtime and the container, so all we have to think about is our code. And what happens here is that the runtime will actually fetch the next event from the AWS Lambda service, pass that event to the code that we want to run, and then once it receives our response, the runtime will send that back to the Lambda service. And the runtime will keep checking for events whilst that service, whilst it is alive. And when there's no more events to be processed, the Lambda service will freeze the container to be thawed out when a new event is ready to be processed, or if no new events arrive in time, then eventually the container will be decommissioned. And so in the case of a custom runtime, this layer of abstraction doesn't exist between us and the Lambda service. Instead, we must call the AWS Lambda service to get events and return our response to the events we process. Luckily, AWS hasn't left us completely to our own devices here. They've given us tools to build custom runtimes that can run on a base Lambda image. And now that I'm 14 slides deep and it's too late for you to leave this talk, it seems to be the perfect time to mention that these native tools are written in Rust. And that's what we're going to use in a lot of the examples today. Before we dive into the custom examples themselves, I wanted to highlight a pattern that became particularly useful as I was developing these custom runtimes, and that pattern is the Three Musketeers pattern. If you work on projects that have lots of disparate tooling or constantly have people being onboarded and offboarded, then the Three Musketeers pattern is a great way to abstract your tooling away from having to be installed on every device. I don't follow it to the letter in this particular example, but it's a handy concept to build on. Basically, it uses Docker containers that package the tooling for consumption on any device that has Docker installed, and I'll go through some of the package tooling that I created whilst putting together this talk. We're also going to use some Rust-specific tools. The AWS Rust runtime for Lambda takes care of all of the pesky calls to the Lambda service, so we can focus on writing just our business logic. And all of the code examples you'll see today won't include any of the boilerplate that this requires, but you can just assume it's there. Cargo Lambda is also a tool used for scaffolding and compiling Lambda functions for use in AWS. And a really cool feature is it allows you to cross-compile your Lambda functions for different architectures. And finally, we have the AWS Rust SDK, which is generally available now. So this allows us to inject functionality into our runtimes to interact with other AWS services. The examples I'm going to give in this talk are very contrived, so we're not going to call out to the AWS Rust SDK, but it's a good tool to have in your toolkit. So the first pattern we're going to approach is the interpreter/external runtime. And this is for languages that either don't compile natively or have an external runtime that is required to execute them, and they aren't natively supported by the Lambda ecosystem. So, what are we going to run? I'm going to use one of arguably the most commonly known ESO-langs for the purpose of this demo, and because we're a family-friendly conference, I'll refer to it as its less offensive moniker, BrainF. It was built in 1993 using Motorola 68000 assembly for Amiga. It consists of only 8 operators, but it is still Turing complete. And this example we have on the right is just a Hello World example. And so how we're going to do this is basically this diagram here. It might be slightly antithetical to how you'd expect it to run, but there's a good reason for that, which we'll get to later. Many interpreters already have C, C++, or Rust bindings. So for example, if you were next door, you'd be hearing about WASM. And two popular WASM external runtimes, WASMA and WASMtime, have bindings to Rust. And this lets us wrap them in a natively compiled Lambda runtime that takes care of all of the pain of calling the Lambda function, Lambda service itself, allowing the embedded interpreter to focus solely on executing the code, not coordinating communication and dealing with all of that sort of stuff. This is a twofold benefit. It decreases the complexity of the code we actually need to write in our target language, and it also reduces any additional dependencies required to call the Lambda runtime with a high-performance native implementation. So this is our handler. I'm not sure if you've ever seen a Lambda handler that looks like this before, but I've forsaken I/O here purely for the sake of my own sanity, but this is the program that we are targeting to run, right? And the Rust to glue this all together is actually surprisingly simple. To wrap it, we just wrap it in the native runtime provided. We include our program with the include string macro provided in Rust, and then compile it into our Lambda. We then, in the function, invoke our interpreter and return our response. In a less contrived example, we may set up our interpreter outside of our function and pass through only subsequent function calls for performance reasons, but this sort of illustrates the point. And so I've got a little bit of a demo of what this looks like when we run this particular example. Hopefully my videos work, so you can see, is this going to play? It is playing, excellent. So we've got our bootstrap, which is our compiled Lambda there. We've got an empty event coming through. We run our brainf program, and we get hello latency conference out the other side of it. And so this does, I'm sure there's someone out there in the audience who's thinking this, right? Just throw the interpreter in a container and push it to Lambda. Why not do that? And there's three good reasons. The first I already touched on about client code complexity, right? The second is that containers on Lambda are significantly more complex, and we will get to a containerized example a bit later. But there's also performance issues when you use containers directly on Lambda as well. And the third point is that because we have the Rust AWS SDK, we can inject host functions into our interpreter, allowing us to extend a language that may not have a native AWS SDK in a language that does. So we can do all of our cool AWS stuff with some glue code in our host runtime, and then inject that into our embedded interpreter. So when would I want to use this, right? This is really useful when you want to run an interpreted or external runtime in a Lambda that's not supported by the existing runtimes. And you want to project host functions inside your interpreter. And of course, a prerequisite to this is that your interpreter has bindings to a language that can support a custom AWS runtime. And those are, at the moment, are Rust, Go, and C. So that is the interpreter runtime. And now we'll look at a slightly different pattern. So we're looking at the external binary runtime pattern. So what are we going to run? Very modern languages in this talk, I'm promising you. We're going to run Fortran, the first commercially available compiled language. Created by IBM in 1957, it's still actively developed, and its last release was in 2023. And it's governed by an active ISO standard. One of the benefits is it is natively compiled. It has native execution speed. It does have 0.1 times development speed, but that might just be a skill issue on my part. And our good friend Dijkstra does have some thoughts on Fortran. Fortran's tragic fate has been its wide acceptance, mentally chaining thousands and thousands of programmers to our past mistakes. So how are we going to do this? This is what we're going to build. We are still going to lean on our trusty native AWS Rust runtime, but we're going to use it to call out to a native binary written in Fortran and packaged up with all of its dependencies. In our Rust binary, we still have the advantage of the full Rust SDK, so we can do any pre-work that our Fortran binary might need, like downloading files or fetching and storing data in some glue code before or after we call our binary. And then our actual handler code written in Fortran will do all of the heavy lifting. So here is our simple handler. There is another part to this, the edit distance function, which you can see on line 12 there. I shamelessly stole that from Rosetta code, and I've omitted it for brevity. But basically, we're passing two strings into our binary and then calculating the edit distance between those two strings. And ignoring the unsafe unwraps in this code, because I just wanted to make it a little bit shorter, here is our wrapper on the Rust side. We pull data from our event payload, pass it through to our binary as arguments, and then pass the output back into our response. To build it, we simply build out our compile script to produce separate binaries for Fortran and Rust applications, and then bundle them together with some shared object libraries for deployment with Terraform. So you can see we're using the GNU Fortran compiler at the top to produce our handler, and then just doing a normal cargo build, and then copying across the shared object libraries all the way at the bottom, and copying across our built artifacts into our distribution folder. And now most AWS Lambdas run on Amazon Linux 2023. And remember that OS-only runtime I showed you earlier? This is where we're going to use it. So we can create a Docker image based on the same environment that runs in Lambda, and then build our application inside that image to ensure that it's going to run on the Lambda environment. And so in a real application, that's what this looks like. So we've got our videos are a little bit slow to play on this internet. Here we go. We've got our bootstrap, our handler written in Fortran, and our shared object libraries. We've got two strings, our source and our target, with only one change between them. If we test it, we should get the edit distance between them. And there we go. At the top, you can see the distance is 1. We can make the edit distance a little bit longer. And I was very slow to click test there. There we go, we now have an edit distance of 6. So yeah, we can run an external binary alongside our main binary that's actually communicating with the AWS Lambda runtime. So why not use bash to pass arguments and interact with the runtime? You can use bash in AWS Lambdas, but you sacrifice two key things. Firstly, you're limited to bash scripting, and with the tools in Amazon Linux, with which there are very few. And secondly, you lose all of the rich SDK integration that you can do beforehand in Rust. So all of that glue code you can write to glue all of this together. So when would I use this? When you've got pre-compiled tools that you want to plug into the Lambda event system, so like a CLI tool that's already been compiled that you just want to download and pass some information to. Maybe you want to download a video from an S3 bucket and perform some processing with FFmpeg. I don't know, whatever you want to do. And it's also handy when you want to do some pre-work before or after you call your binary, such as to do operations in S3. So that brings us to our next runtime, and this was my favorite one to program. It probably took me the longest. So what are we going to run? And you might have already got a spoiler for this one a little bit earlier, but we are going to run COBOL in an AWS Lambda function. We talked about Fortran as the first commercially compiled language. Grace Hopper was integral to the development of early compiled languages and one of the inspirations for COBOL. It was the original low-code tool. It was meant to be written in business logic. It was self-documenting. It's the future. I still believe we're going to be using COBOL in 5 years. Pioneered by the US Department of Defense because they were switching architectures and they wanted something that could compile to different hardware targets. And believe it or not, it still handles trillions of dollars a day in the financial sector. The original IDE for COBOL, I'm not sure how visible it is up there, but was a sheet of paper on the right there. I didn't check whether it has a Copilot or cursor extension. Jury's still out. Don't fact check me. But yeah, we'll see. And our good friend Dijkstra also has a quote about COBOL. The use of COBOL cripples the mind. Its teaching should therefore be regarded as a criminal offense. So sorry all, I've got to go straight to jail after this. Following a similar pattern to our external binary runtime, we're now going to do something very slightly different. If our language can be compiled to a native object that complies with the C calling convention, we can compile native code directly into our native Rust runtime. And because Rust can also be compiled to the C calling convention, we can actually go the other way too. So we still have all of our nice glue code in our Rust runtime, but now we have the runtime also compiling in our target language. To make this work with COBOL, I had to also package up a whole heap of dependencies into a container. So this one I deployed as a container image based on Fedora, mostly because the GNU project was available as a DNF package on Fedora, and I didn't want to compile it from source because I'm just a little bit too lazy to do that. So our COBOL handler is a simple hello world. I didn't want to get any more complex than that. Once I got it working, I was like, I'm not touching this again. Also, please don't knock Python's significant white space requirements until you've written COBOL. It is absolutely horrendous. So aside from the COBOL, we also had to do a quick little C function to enable the COBOL-C interop. And then in Rust, we defined two foreign functions, which are the two functions we just defined in COBOL and C. So our initialized COBOL function and our handler. Our Rust handler is a little bit more complex, mostly because I made the mistake of making a demo with string manipulation. But basically, we're taking a name from our event payload, and we're putting it into a buffer. We then initialize another buffer for our output, and then call our COBOL handler. Our output buffer is then marshaled into our response to Lambda. To build this one, we first needed to compile our C and COBOL code with the GNU COBOL project, and then we run a normal cargo build with a bit of a twist. We add a build script to our cargo build to compile our object files into an archive file and then link it into Rust alongside libcobol. And to do this, we build a build container containing all of the tools required to build our project, which in our case is basically just GNU COBOL and Rust. And then we build a separate run container without the weighty Rust toolchain and push that container to a registry and deploy to Lambda. So this is what this looks like. We don't get the little code view because this is now an image-based Lambda, but once the video loads, there we go, it's running. So yeah, no code preview. We can hit test. I've got value 1 in there, but to honor all you guys, I'll put latency in there. And we can hit test, and then we get, there we go, hello latency out the other side. So now we've got COBOL successfully running in Lambda. When would I use this? And I'm not saying when would I use COBOL, because the answer is never. But when I would use this is when I have a language that compiles natively and conforms to the C calling conventions. And it's really useful when we want to plug SDK functions into a language that has none. And it's also useful in performance-critical applications because everything's natively compiled. It's all part of one binary. You don't have any of these handoffs between processes, so you can get pretty good performance out of that. And that hello world that I had in COBOL outperforms my Node.js hello world. So, language of the future. The final pattern we're going to look at is a self-contained runtime. So, what are we going to run? This one's a little bit less interesting, but still a fun one, I find, because I had to write all of the glue code myself. But we're going to run OCaml. It's a functional-ish language with native performance. I say functional-ish because you can do imperative stuff in it. It's used in high-frequency trading, and it's used to bootstrap other programming languages. Funny fact, the initial Rust compiler was actually written in OCaml as well. So there we go. There is a link. As much as it pains me to deploy a Lambda that doesn't have Rust in it, there is a link. And in this model, there's no Rust handholding, right? So here we are. Instead, we make all the calls to the Lambda service ourselves. And this will run in one of the default Lambda containers, so that OS-only provided runtime with no additional wizardry required around creating extra containers. So to start with, let's look at our handler. We take a JSON object which has a property name. We then remove all the vowels from it and return it to the caller. I don't know about you, but my name is about 60% vowels, so I'm looking forward to being unencumbered by them with the help of my new Lambda. There are essentially 3 other things we need to do to make this work. The first thing we need to do is make a call to the AWS Lambda Runtime API to get the next event. And that's what this quick little bit of functional programming is doing with all of my terrible piping involved. We also need a way to send responses back to the Lambda Runtime API once we processed events. And so that's what we're doing here. We're just taking a response JSON and a request ID and passing back to the invocation API the response JSON that we've created. And then finally, we need to pipe that through our handler in a continuous loop until eventually Lambda comes along and unceremoniously kills our container. Building this one is actually quite simple. We just leverage the Dune build system to create a native binary. And of course, for maximum compatibility, we are building all of this on Amazon Linux to ensure compatibility with the environment that we'll eventually deploy this to. So yeah, the build tools are written on Amazon Linux too. So here's a quick demo of this one. Once again, suffering video loading. There we go. We've got our bootstrap handler. Hit test. I've got my name in there as the test event. Hit the test function. And there we go, 60% of my name removed. Much lighter. Cool, and so that is our fully self-written Lambda runtime running. So when would I use this? If you are compute bound and you're basically just running like a business logic workflow in Lambda, this can be really useful. It's really handy when there's no other external AWS dependencies that you need to call, because you won't have the crutch of an AWS SDK to lean on to do this. It can also sometimes be easier to just reason in one language. So there are arguments for building it in one language just because you don't have to switch between Rust and something else. And also, if your language doesn't play nicely with foreign function interfaces or doesn't conform to the C calling convention, then this is a good opportunity. So back to our overview, we went through what custom runtimes are. We went through the interpreter/external pattern using an external binary. We then used a library shim to run COBOL. Still makes me shudder at the thought of writing that. And then we ran a self-contained example. So hopefully you all managed to learn something from this talk. If you would like to judge my code and see how bad I am at writing all of these languages, feel free. That's a link to the GitHub repo, which should be public. There's no README in it. Consider this talk the README. But yeah, there's make files. So just read the make files. It's self-documenting, I swear. Yeah, so hopefully you all enjoyed it. And of course, I would love some feedback on this. We also have a couple of talks coming up after lunch. But after this, yeah, we do have the lunch break. I don't want to keep you all from lunch. We are a little bit over time. If anyone has any questions, you can either come up to me directly or catch me at some point throughout the rest of the conference. But thank you all for listening to my talk.